Hi everyone, we're going to be looking at the nature of light today. So the nature of light is actually consistent of waves. So waves, whenever you're looking at something, can be, we're going to use a couple of new vocab words. So one of them is amplitude. And amplitude just shows you how high the crest is from the baseline. Okay, so again, the amplitude is how high a wave goes. You can also figure this out by looking at how low a wave goes. And so if you are looking at how high it goes, you're looking at the crest, whereas if you're looking how low it goes, it is the trough. Now the crest and the trough are usually, for this class, going to be equal to each other. We can also look at how long the wave is, and that's called wavelength. And we can figure out how long a wavelength is by looking at crest to crest or looking trough to trough. Both of them will give you the same number, but it depends on what your question is giving you. If it gives you if it only gives you two crests, at that point you would have to use the crests. Wavelengths is also going to be represented by a new symbol, and it is called lambda, and it kind of looks like a backwards H a little bit, and that simply is looking at how far apart those two crests are. And we usually measure our wavelength in meters, and remember that is the symbol M. We're also going to be looking at how often the waves are going to be happening. So that is called the frequency. And frequency is denoted by this symbol, which is that of nu. And it is telling us how often a wave passes a specific point in a given amount of time. And that is going to be in a new unit called hertz. Whoops. So that would be Hertz. Another way of writing it is whatever number it is over seconds. So if you were to look at this example here, you have to count how many times a full wave goes past our line here. So if you wanted to count, we have a full wave, 1, 2, 3, 4. So we would probably have 4.5 waves here, so it would be about 4.5 hertz. And whenever we have both the frequency, which again is in this new Greek letter, which is called nu, and our wavelength, they are related. If you were to multiply them, you would actually get the speed of light. And the speed of light is 3.0 times 10 to the 8th meters per second. So this number never changes. So the nifty thing about that is we can always determine an unknown variable as long as we have at least the wavelength, or if we have the frequency, then we can figure out our missing variable. So that means that the frequency and the wavelength are inversely proportional. That means as one goes up, the other one must go down. So let's take a look at our example here on the left. If we have a low frequency, that means that our waves aren't happening very often. That means that we have a large wavelength. So our frequency, which is again in our nu, is low. That means our wavelength must be high, because the product of those two must always equal 3.0 times 10 to the 8th meters per second. Now let's take a look at something else. Where we have high frequency, we get a very, very short wavelength. So again, our nu went up. That means our frequency must go down, and that will still give us the speed of light being 10.8 meters per second. So you could see this inverse relationship. As one goes up, the other one will always be going down. Now, according to our wave model that we've been looking at, we are also going to say that we have electromagnetic waves. And electromagnetic radiation can take place in a few different forms. The first one that was kind of discovered was our radio waves, and that's the stuff that we hear in our car. We also have microwaves, which are going to be the things that cook your food. We then have infrared waves, and that's right before we can see things. Then we get our visible light. That's my favorite part. Finally, we get ultraviolet waves. That is going to be the stuff that gives you a sunburn. X-rays lets you see your bones, and gamma rays, which are used in like chemo radiation. So whenever you have these different wavelengths, you are also going to get a spectrum of colors. So the reason that we get different colors is because of how fast or how slow the light is moving. So in a visible spectrum, the red is going to have the longest wavelength. So if you have a long wavelength, that means your frequency must be very low. And that's true of again, because of the equation C equals lambda nu, that's going to be true for all of our examples. If one goes up, the other must go down. So whenever we're looking at a prism is going to separate light. And whenever we're separating light, you're going to get them into their lowest frequency and their highest frequency. And we can actually use this prism to see how fast and how slow different particles are moving. Whenever we are putting this on something similar to a number line, it looks a little bit like this, where we have our radio waves all the way down here on the left. Those are going to have a very, very long wavelength, meaning their frequency is very low. And this symbol right here is just another way of saying this number over S, or hertz. And you can see as we go to the right, the amount of energy is actually increasing. And we can kind of figure out how much energy something has based on what happens to our body. With radio waves, nothing happens. I mean, we don't get any damage whatsoever, whereas gamma rays can go through our body and target cancer cells. So there's a big difference between how much energy there is whenever you're looking at this spectrum. You can also see that the lowest energy in visible light is our red, and our highest energy is in purple. So we'll actually be able to use that information to figure out some problems later on what color should be emitted. It's pretty nifty. Now, anytime you're looking at an atomic emission spectra, there are a couple of interesting things you get to. So different elements have different colors that are going to be shining through. So things like a neon sign that lights up at night will be bright colors, whereas helium is going to be this like yellowy color here. And whenever you put it through our prism again, instead of getting a nice spectrum like we did for light, we only get certain parts of our rainbow. And the reason for this is electrons can only move from one energy level to another. Remember the idea of the ladder, where we have different energy levels and they start getting closer and closer together as you get closer to the top? Well, this is a visible way of showing that idea. Electrons can only go from one energy level to the next if there's enough energy. So each element actually has a different atomic emission spectra because of the and electrons being quantized. Meaning, again, you have the idea of going from one level to the next. And if you don't have enough energy to get to that next rung of the ladder, you're going to fall back down and stay on this rung of the ladder before going to the next section. So the cool thing about this is no two elements are going to have the same emission spectrum. The reason for that is no two elements have the same electrons. So if you were to do the electron configuration, you would see that you have different numbers of electrons in every element. So that causes a different atomic emission spectrum for every element. So before we go, I just want to try out a problem to see if we can calculate the wavelength of a yellow light emitted by a sodium lamp. So stuff that isn't really important at the moment. If the frequency of the radiation is that amount. So remember, we have C equals lambda nu, where C equals 3.0 times 10 to the 8th meters per second, and that is the speed of light. Lambda is our wavelength, and nu is our frequency. So just like before, let's write out exactly what we know. C, lambda, and nu. C equals always 3.0 times 10 to the 8th meters per second. Lambda, hey, it says calculate the wavelength. That says that we do not know that number. And nu is 5.09 times 10 to the 14th hertz, or I like to write it as per second. Okay, so if we were to take this and plug in our numbers, I'm just going to erase this so we have a little bit more space. It would be 3.0 times 10 to the 8th meters per second equals lambda times 5.09 times 10 to the 14th per second. So just like in algebra, you have to do the opposite operation to get our lambda by itself. So you would divide by 5.09 times 10 to the 14th. So there we go. And you have to do the same on both sides. And this allows us to cancel our seconds. We're going to be left with meters. And our answer would be, from our calculator, 5.89 times 10 to the negative 7th meters. And if you would like, you can go through this in a little bit better of a little bit cleaner, neater way. So here is the same exact information. This is just a more specific number, but when this class, we're going to use 3.0 times 10 to the 8th meters per second. And that they decided to rearrange their equation before plugging it in. Both ways work. But it will also give you the exact same number. So whenever they plugged it in, they got the same number as we did, canceled out their units, and got 5.89 times 10 to the negative 9th. One before we go, we have what is the frequency of a red laser that has a wavelength of 676 nanometers. So again, we have C equals lambda nu, and this is our wavelength. And here is our frequency. And this, of course, is our speed of light. And let's write down our knowns, C, lambda, and nu. We know that C is always going to be 3.0 times 10 to the 8th meters per second. This time we are given wavelength. So we have 676 nanometers, and we don't know our frequency. But if you take a look, our units don't match. So if you wanted to convert that, it would be 676 times 10 to the negative 9th meters. And then once again, we just plug everything in. So C equals, 3.0 times 10 to the 8th meters per second equals 676 times 10 to the negative 9th meters times nu. Divide that out. I get 4.43 times 10 to the 14th per second. Sorry about that. Or hertz. So if you need to have that, it's in your PowerPoint as normal, and I will see you next time.